Next, we'll be looking at matrix subtraction. Now, as I had mentioned in matrix addition, the very important statement is that the two original matrices on which we'll be adding or doing the operations essentially for addition and subtraction at least, the matrices need to be of the same dimension. For the same criteria essentially holds for subtraction as well. That is, the matrices need to be of the same dimension. So if I am talking about a matrix A which has 3 cross 2 dimension, and I'm talking about another matrix B which has 5 cross 6 dimension, we won't be able to operate addition or subtraction for these two matrices. The two matrices need to be of the same order. So let's go back to the notations we had discussed when we were talking about matrix addition. So if we have Aij, which has dimension m cross n, and Bij, which represents the B matrix, has dimension m cross n, then if we subtract B from A, that is, if we make the operation A minus B, then let's suppose we get a result D. The dimension of D again will be as before, n cross n. So the original matrix's dimension gets carried forward into the resultant subtracted matrix. And what we essentially do is pretty similar to the addition operation. In addition operation, as we had added each corresponding element of the two original matrices, in subtraction again, we will be subtracting the corresponding elements from the two original matrices. So if we want to do A minus B, then from every corresponding A element, we will be subtracting the corresponding B element. And again, vice versa, if we want to do B minus A, then from every corresponding D element, we'll have to subtract the A element. So that gives me D equals A minus B. Another thing that we need to note is this matrix subtraction can also be defined in terms of matrix addition. So let's suppose I have a matrix A and a matrix B, and I want to subtract B from A. I can either do it by matrix subtraction, that is subtracting the elements of B from A, or I can construct another matrix minus B, that is, we'll be multiplying, or in this case, let's just simply say I'll be placing or putting a minus sign in front of all the elements of B matrix, and I'll be adding that. So let's suppose I have 1, 2, 3, 4 as one matrix, and I have another matrix, let's say 5, 6, 7, and 8. Now, if I want to subtract 1, 2, 3, 4, this matrix from this matrix, I can either say 5 minus 1, 6 minus 2, 7 minus 3, 8 minus 4, or I can actually say I am adding these two matrices. So I can say 5 plus minus 1, that again gives me 5 minus 1, 6 plus minus 2, that again gives me 6 minus 2, 7 plus minus 3, which is again 7 minus 3, and 8 plus minus 4, which is again 8 minus 4. So you can interpret it as normal algebra suggests that addition and subtraction is essentially a different form of addition, where the sign has been interchanged. That is, A minus B is the same as A plus minus B. So you can interpret matrix subtraction as a step down from matrix addition as well. So let's look at an example. So let's suppose I have matrix A and B as before. So I have A matrix, that is 23, 46, 2, 90, and I have matrix 5, 2, 30, and 5 to represent the B matrix. Then D will be 23 minus 5. The element corresponding to the first row and the second column, that is D12. So let me just mark this here. This one is D11. So this is D11 because this corresponds to the first row and the first element. This element is D12 because this corresponds to the first row and second column. So D12 will be A12 minus B12, that is 46 minus 2. D21 will be 2 minus 30, that is 2 minus 30 over here. And finally, D22 will be A22 minus B22, that is 90 minus 5. So I have 23 minus 5, 46 minus 2, 2 minus 30, 90 minus 5. So resultant will be 23 minus 5, that's 18. 46 minus 2, that's 44. Or we also have 2 minus 30, that's minus 28. And 90 minus 5, that's 85.